Hello, dear colleagues. My name is Artem Andreev, and the name of my presentation is Enhancement of Land-Cover Classification by Geospatial Data Cube Optimization. The input data for land-cover classification is presented in the form of Geospatial Data Cube. For specific classification tasks, the cube can comprise numerous layers, including multi-temporal data, multi-source data like optical and radar, and also multiple ancillary data. For example, data on geomorphology, hydrology, or phenology. Uh, so such a cube could be redundant. Moreover, data redundancy leads to the following problems. First, the processing of such data cube has high computational complexity. Second, the layers could be either incorrectly created or irrelevant to the selected thematic task. It results in low train sample separability, which causes a decrease in classification accuracy. Now let's discuss the widely used approaches to reduce input data. There are principal component analysis, minimum noise fraction, noise-adjusted principal components, independent component analysis, non-negative matrix factorization, and the last one is spatial spectral decomposition. However, a common disadvantage of the considered approaches is that they do not consider the trained sample's structure and the selected classifier's specificity. When I'm talking about the trained sample structure, first of all, I mean the training sample separability. And this slide is about the developed optimization technique. The developed optimization technique implies selecting the cube layers with the highest trained sample separability among other options. And the aims of this technique are reduction of geospatial data cube size by discarding the extra layers, enhancement of the land-cover classification by increasing the separability of the trained sample. Since we are discussing the optimization technique, the object function should be assigned. Here, object function of the optimization technique is the developed separability index of the training sample. Also, it could be named SIDS. On this slide, the algorithm of assessment of the training sample separability is presented. On the left side, you can see the flow chart of the algorithm. This algorithm contains 4 steps. Step number 1, training the classifier by the input training sample. Step number 2, the classifier is used to classify each signature from the training sample set. And step number 3 is the formation of the confusion matrix for the obtained classification. And the last step implies calculation of the separability index based on overall accuracy. Also, you can see the simple formula of the calculation of this index. And on this slide, the algorithm of the developed optimization technique of the geospatial data cube is present. This algorithm is an iterative procedure. Each iteration contains 3 steps. Step number 1, formation of new cubes by discarding of one layer from the initial cube. It means that if the input data cube has n layers, then it will be decomposed into n cubes with n minus 1 layers. And step number 2. This step implies calculation of separability index for each obtained data cube. The last step is the selection of the cube which has the highest SIDS value among all other cubes. Then the next iteration will use the obtained cube instead of the initial one. The stopping criteria of the optimization are decrease of the separability and also the technique will be stopped will stop if only one layer left. And the result of this technique is the optimal geospatial data cube with the highest separability value among all other cubes. To test the effectiveness of the developed technique, an experiment was conducted. The study area is depicted on this slide. It is Shatsk National Natural Park. For the land-cover classification, 6 classes were selected, namely artificial surfaces, tree-covered areas, grasslands, agriculture areas, water bodies, and wetlands. The input geospatial data cube contained 222 layers. There were 4 multi-temporal Sentinel-2 spectral images, where each image contains 10 spectral bands and 45 spectral indices. Also, the digital elevation model and values of slope were used in the initial cube. And also, as you can see, after the optimization, the cube contained only 40 layers. This is more than 5 times less than in the initial geospatial data cube. The experiment applied tool and cover classifications, one with the initial cube and one with the optimized cube. And as you can see from this slide, the classification method was the same for each classification, and it was Mahalanobis distance. And overall accuracy for the initial classification was 90%. And for the classification of the optimized data cube was 94%. And kappa was 86% for the initial one, and for the optimized one, it was 92%. And now the conclusion. In this article was presented method to assess the training sample separability in terms of its structure and the selected classifier. Also, optimization technique of the geospatial data cube based on the training sample separability. The conducted experiment indicated, first, classification enhancement, namely increase in overall accuracy by 4% from 90 to 94%, and the kappa coefficient by 6% from 86 to 92. And the second is the reduction of the data cube size by 5.55 times from 222 to 40 layers. Also, I can admit that further research should be aimed at the technique application in other study areas and thematic tasks. And the spability assessment of the trained sample could be extended by additional criteria. For example, the kappa coefficient could substitute overall accuracy as the basis of the developed separability index. Thank you for your attention, and that's all. Goodbye.